Hi, welcome back to Introductory Statistics. This week we're going to talk about the accuracy of averages. We'll cover chapter 23 from our textbook. Okay, suppose we have a box, and in this box we have numbers from 1 to 7, and say that we're going to select 25 tickets from this box, and we're going to do it with replacement. Each time we take a ticket out, we put it back. And so we can simulate this process by writing, say, a computer program, and say we run the program and we get the following 25 tickets. We add up the sum, we get 105, and the average of these tickets is 4.2. We do this again the second time, get a different list of 25 tickets, find the sum, which is 95 this time, and say the average, in this case the average is 3.8. So the point here is that as we keep doing this, we notice the sum will vary, and so will the average. And in the previous section we talked about how to find the error associated with this sum. So in this section we're going to talk about how to find the error associated with the average. And so let's do this example with 25 draws, and we want to determine the average of the draw, what the average of the draw would be, and the error that would be associated with this draw. Okay, so we've the average of the box we can compute is turned out to be 4, and so we expect that the average of the 25 draws will be the same as the average of the box, which is 4. So now we have to find the error, the SE, for this average. Okay, so again, if we were to redo what we did in the previous section about finding the expected value for the sum of the 25 draws, remember that we had a formula that says that if we take the number of draws and we multiply by the average, then we get the expected value for the sum. So in this case, we take in 25 tickets, so 25 times 4, which is the average of the box, we get 100. So that means that if I take out 25 tickets, I expect my sum to be 100, the sum of those 25 tickets. And we saw that that was similar. In the previous example, we saw that we got 105 one time, we got 95 another time. So we expect the value of the sum to be around 100. Now to find the SE of this sum, we had to use the formula, the square root of the number of draws times the SD of the box. So in this case, we can compute that the SD of the box is 2. Again, we talked about that previously. And so using the formula, we find that the SE for this sum is 10. So that means that if I pick 25 tickets from this box, I expect the sum to be 100. I expect the error to be about 10 or so. Now we've done this already in the previous section, so now, but the question in this chapter is about what is the average of these draws. And so how do I find the average from the expected value for the sum? And so it's actually really simple. We just again, the sum of the 525 draws is 100 plus or minus 10 would be the error. And so to find the average of the 25 tickets, we simply divide everything by the number of tickets, which is 25. So divide everything by 25. So we get that the average of the 25 draw should be around 4, and then the error associated with that average is about 0.4, which is the error for the sum, which is 10 divided by 25, which gives you the 0.4. So in summary, here's the formula that we need to use for this, and it's really the same formula as we had before when we talk about sum, except now we have to divide everything by the number of tickets, the number of draws. So when I draw a random from a box, the expected value for the average of the draw is the same as the average of the box, which makes sense because the average of the box is the data for the box, and so when I pick randomly, we should have that the draw should reflect the composition of the box. And then for the SE of the average, then we simply take the SE for the sum, which we know how to find from the previous section, and we simply divide that by the number of draws. And here's a very important fact. When drawn at random from a box, the probability histogram for the average of the draws follows the normal curve, even if the contents of the box do not. And so if I put this histogram into standard units, we can use the Z table to calculate probabilities. So this fact is from chapter 18, which we haven't covered, but we're going to take this statement as a fact. We won't and then we're going to apply it to the following examples. So say I pick 100 draw from a box for the same box as earlier with replacement, and so we're going to find the average of the draw and the expected value for the average, as well as the standard error for the average. And then we want to calculate the probability that the average of the draw will be more than 4.2. So same as example 1, the sum of the draw will be 100 times the average of the box, which is 400. So if I pick out 100 draw, I expect my sum to be about 400. The SE for the sum is root of 100 times 2, which is 20. So that means that if I pick out 100 tickets, I expect the sum to be 400, the error to be around 20 or so. Again, to find the average, we divide everything by the number of draws. So 400 divided by 100 is 4. The error 20 divided by 100 is 0.2. So that means that if I pick 100 tickets, that I expect my average to be 4 and the error to be about 0.2. To do part B of this, to find the so if the average is a 4 and the error is about 0.2, then what's the chance that the average of the draw is at least 4.2? So this is where we convert into a Z table problem, a Z normal distribution problem, convert everything to standard units, and use the Z table. So again, the expected value for the average is 4, and the SE is the standard error is 0.2. So that means that if I were to draw this out, I want to know the probability that I get 4.2 or bigger. That means that if I convert those into Z-score or standard units, the average 4 becomes a 0, and then 4.2 is 1 SE away from the average. So that would, if I convert it to a Z-score, that will convert to a 1. Again, the math behind that is 4.2 minus the average, minus 4, which is 0.2, divided by the SE, which is 0.2, gives you a 1. So to find this answer, I have to do is figure out what's the probability that I get my Z-score is 1 or bigger. That's exactly from the Z-table problem, and I get that the probability is 16%. Okay, now we're going to flip this and talk about something called the sample average. So in the previous couple slides, we talked about if we have a box, I know about this box, and we want to pick some tickets from this box that I know already. But that's not very useful. What's more useful is go in the opposite direction, meaning that I have a box that I don't know anything about, the composition I don't know, and I want to estimate. I want to infer something about the composition of the box by looking at the data from the composition of my sample. So I pick out a bunch of tickets, and this is like essentially polling. If I pick out some random sample and I look at the data of the sample, can I get that data to tell me something about the composition of the box? And so we're going to take a sample from this box, and we want to estimate in particular the average of the box from the average of the sample, and then we want to know about the errors associated with this this average. So here's a good problem. Suppose we have a city manager who wants to know the average income of the 25,000 families living in the town, and so we do a survey, ask a survey organization to do a poll, and they sample 1,000 random families, and then ask them to answer questions about the income. So from the data, say that the total income of the 1,000 sample families turned out to be 62,396,714. So from that data, we can find the average of the sample of these 1,000 families. Divided by 1,000, we get that the average income from those sample families is 62,400. So that means we can use that data to say something about this, the average income of the town. So we estimate the average income of the 25,000 families to be 62,400. Now, of course, this estimate has an error to it, because when we picked out 1,000 family, it could be any 1,000 family, and if I do the poll again, it could be a different 1,000 family, and so there's a chance error here. Depends on who we pick. So we want to find the error, the chance error associated with this data. So we want to know what is the error. Okay, so this is the same problem as before. We have 25,000 tickets. We don't know anything about these people. We pick a sample of 1,000, and we're hoping that the sample can tell us something about the population. Okay, to find the SC for the sum, again, everything is always back to the SC, the error for the sum. So the formula of the error sum is the square root of the number of draw times the SD of the box. So we're picking 1,000 tickets, so square root of 1,000 times SD of the box. But again, before we saw this bootstrap method before, where we need this SD of the box, but we don't have the SD of the box. We don't have any data about the box. And so to do this, we look at the SD of the sample and use that to estimate the SD of the box. And so because we pick out 1,000 family, we have the incomes, we can compute the SD of the incomes. And so let's say that from this data we get that the SD of the income is 53,000. That tells you the spread of the income of the 1,000 family that we survey. So we're going to use 53,000 as the SD of the box to estimate the SD of the box. So now we apply the SD formula for the sum, which is root of 1,000 times 53,000. We get about 1.7 million. Now to find the SD for the average, we simply divide that by the number of sample, which is 1,000. So we get that the SD for the average is 1,700. So this says that if this tells you how much the error that is associated with the average of our sample. So this means that we estimate that the average income of this 25,000 families is about 62,400, where the error is about $1,700. And in the previous section we talked about the confidence interval and how this interval can help us figure out trap the population average. And so we saw before that if I take the error and I multiply by 2, go 2 to the right, 2 to the left, we get an interval that represents the 95% confidence interval for the average income of all the families. In other words, 62,400 times plus or minus 2 times 1,700 will give you a range between 59,000 and 65,800. Again, I'm adding, subtracting 1,700 on both ends of the average. And so that means that here's the interval, 95% confidence interval. We are 95% confident that the population average is trapped between this interval. So meaning that if I were to repeat this survey 100 times, then 95% of the time this interval will contain the population average, and the other 5% this interval does not contain the true population average. So that's how you interpret that interval. Here's another example. Say we pick a random sample of 400 people aged 25 and over, and we want to figure out the total years of education that they have gone through, and say that the total years is 4,635. From that we can find the average education level in terms of years. Divide by 400, we get 11.6 years. So that means that this is the sample from from the sample of 400 people. And let's say that the SD of the sample is 4.1 years. Now we want to find the 95% confidence interval for the average education level for all people over 25. In other words, from our sample of 400, from our poll, can we say something about the average education level for everyone from the town? So again, so we always do a box model. We have a box we don't know anything about. We want to pick 400 people from this box. And so it's just like before, we want to find the SE for the average of the draw. So we start with the SE for the sum, which is root of 400 times SD of the box. Again, this SD is unknown, so we're going to estimate it by using the SD of the sample, which is 4.1. So this will give us the SE for the sum, which is root of 400 times 4.1, which is 82 years. So that means that if I pick 400 tickets from this population, my sum 82 is a measure of how big the error is from the sum that we got earlier, which is 4635. we take this SE, we divide by 400 to get the SE for average, which is 0.2 years. So this says that we expect that the average of the population should be about around 11.6, plus or minus 0. Well, 0.2 years is the error, but if I want the 95% confidence interval, I take the average, which is 11.6, and then I take the SE error for the sum, multiply by 2, and then add and subtract that from the average. So that means that this 95% confidence interval is between 11.6 plus 0.4 and 11.6 minus 0.4. And so this says that I'm 95% confident that this interval will contain the true average of education level for all people in the town. Okay, so we have a bunch of SE, so let's do a quick review here before we end. Different SE and how we interpret it. And then these are all in terms of, you know, how we want to survey, depends on what kind of operation we're taking. And so, for example, we start out with the SE for the sum. So this means we're picking out, without replacement, many tickets from a box. We want to know the sum of it, and we want to know the error that is associated with that sum. And so that formula is root of the number of draws times the SD of the box. And then if I want to pick up a bunch of tickets, I want to know something about the average of it. Then how do I measure the chance error? Well, the SE for average is simply taking the SE for sum that we did earlier, divided that by the number of draws. So that gave us the SE for the average. So everything really comes from SE for sum. Once I know the SE for sum, I can use that for every other SE. How about the SE for count? This is where I have maybe a survey and I want to count the number of Democrats or Republican. So this is good for surveying. And so the SE for count is the same thing as the SE for sum, except that my sum is from a box of 0 or 1. Maybe 0 if you're a Democrat, 1 if you're a Republican. So maybe we're trying to count the number of, well, actually 0 if you're a Republican, and then sorry, let's say that again. 1 if you're Republican, say you want to count the number of Republicans, 1 if you're Republicans, and 0 if you're not Republicans. And so maybe I'm trying to count the number of Republicans in the survey, then I can do a box of 0 or 1, and then the SE for sum would be the same thing as the SE for the count. And then we also talk about SE for percent, which is the same. Again, this is we're taking the SE for count, which is the same thing as SE for sum, and we divide that by the number of draws, and then multiply by 100% to convert to a percentage. So really, all these things come from SE for sum. SE for average is SE for sum divided by the number of draws. SE for count is SE for sum, just from a different box. Then SE for percent is just taking SE for sum or SE for count, and then divide by, and then convert that into a percentage. So in the last few chapters, we talked about, you know, either going forward or going backwards from a box. You know, going forward is, if I have a box, I know the composition, I pick some tickets, you know, then I should say something. I should say something about the error associated with randomly picking out tickets from this box. But that's not so useful. Going backward is what's useful. In other words, I have a box, and the composition of this box is unknown, and I pick a bunch of tickets, and then I look at the data from the tickets, my sample, and then I'm hoping that the data from the sample can help me infer something about the data of the population. And that's where the utility of all these math come from, is when we do polling. You know, I can't ask everyone in my state how they're going to vote, but I can do a small sample, and if I do it well, if my sample are random, then a sample of only 1,000 people can say a lot about how the entire state of, say, 10 million people will vote. And that's a lot of power. That's why, you know, we can do that gives us a lot of power to get information from such a small sample to say something about such a big population. Okay, thank you very much for listening.